Okay, thank you. So, welcome to part 2 of today's lecture. I want to make one more comment related to the earlier part. Right. So, one way to see if you think about the integer cone, at least for 3 graphs, 2 connected 3 regular graphs, this is the same as saying whether the graph is 3-edge colorable or not. All ones vector belongs to the integer cone if and only if the graph is 3-edge colorable. And in general we know that such a graph is either 3-edge colorable, otherwise it is definitely 4-edge colorable. And the set of graphs, the set of 3 graphs that are not 3-edge colorable are generally known as snarks. Often people add more conditions, but one of the most primitive definitions, if I may call it, of a snark is a 3 graph that is not 3-edge colorable. Therefore, its edge chromatic number is equal to 4. So this is a large set, snarks. So there are a lot of 3 graphs for which the all ones vector does not belong to the integer cone. One of the snarks is the Peterson graph, the smallest snark. But somehow if you relax the problem, you go from the integer cone to the lattice, then the other snarks are no longer snarks. They are okay. Only the Peterson graph is the problem there. Right? So if you consider this relaxation, then all the other snarks are actually somehow good. That's what I mean. For all of them, the all ones vector, okay, here I should restrict myself to bricks. I should restrict myself to 3 connected. I should restrict myself to cubic bricks. Right? Because 2 connected 3 regular graph. So if I restrict myself to bricks, snarks in general are bricks. If you impose essentially 4-edge connected, which is a standard definition included in the modern definition of snark, then snarks become bricks. Right? So all those bricks are actually fine, except for the Peterson brick. The smallest snark is somehow the worst snark, and in some sense the only snark if you consider the lattice instead of the integer cone. Right? That's one way to think about how important the Peterson graph is. Like, not only is it the smallest snark, it is somehow a very, very fundamentally bad snark, or good if you like, I don't know. Is that making sense? Okay. Anyways, I wasn't super precise, but anyways, I hope I conveyed the point. So okay, enough about all those things. Let's go back to some matching covered graphs, and we will relate some of the things we are talking about to the perfect matching polytope. So we begin, formally speaking, solid graphs, and in particular we'll focus on solid bricks, and you will see why. So solid matching covered graphs may be viewed as a generalization of bipartite matching covered graphs in the following sense. In bipartite matching covered graphs, separating cuts are the same as tight cuts. Yeah? A cut is separating if and only if it is tight. Turns out there are more graphs where this happens. Those are the solid graphs. A matching covered graph is solid if and only if definition, every separating cut is tight. A solid graph, okay, maybe I should write a matching covered graph is solid if every separating cut is tight. In particular, if you want to think about it as a Venn diagram, the bipartite matching covered graphs are a subset of the solid graphs. By the way, when I say solid graph, I mean solid matching code graph. I'm defining solid only for matching code graphs. But I can't do that with bipartite because, of course, if I say bipartite graph, I could mean any bipartite graph because it's a very common term, right? So, yeah, okay. But this set is not empty. Can somebody give me an example? What is the smallest solid matching code graph that is not bipartite? K4. The smallest creature here is K4. Yeah? Okay. But there are many others. For example, can we define a solid brick now? Of course, you can say it is a brick which is solid, but can we also define a solid brick in a different way? For example, a brick is a non-bipartite matching code graph that is free of non-trivial tight cuts. Can we use a similar language to define solid bricks? Free of non-trivial separating cuts. A solid brick is any brick that is free of non-trivial separating cuts. Yeah. We have seen in a previous chapter. Okay. Corollary 4.10. Recall. I mean, I don't expect you to recall the number. If you have a non-trivial separating cut, well, I don't need to say non-trivial. If you have a separating cut in a matching code graph that is not tight, then you can say something about the two shores. So, G is a matching code graph, C is a separating cut that is not tight. Then each shore of C, if you consider the subgraph induced by the shore, what can you say about it? Contains an odd cycle. If a shore is bipartite for a separating cut, then actually that cut is tight. That is something we discussed a long time ago. Then each shore of C induces a non-bipartite subgraph. Therefore, it immediately follows that the graph has a pair of vertex-disjoint odd cycles. This is equivalent to saying, I'll write on the board equivalent. Implies that G has a pair of vertex disjoint odd cycles. Yeah. For the sake of fun, we will say a bicycle is a pair of vertex disjoint cycles. Yeah. And we will call this an odd bicycle. So what is a bicycle? A pair of vertex disjoint cycles, and now I can simply say that this is the same as saying G has an odd bicycle, by which I mean that both the cycles are odd. If both cycles are even, I will call it an even bicycle. If one is odd, one is even, I will call it a mixed bicycle. You probably won't need a mixed bicycle in this course, you'll see. Well, the only bicycle you will need is to bicycle to the classroom. Okay. Alright. So, now let's go back to more examples using this observation. One way to see that K4 is solid is to just observe that K4 does not have two vertex-disjoint odd cycles. Therefore, it is solid. But now you can talk about other families. Can you tell me other families of solid bricks using the fact that they basically, if they don't have an odd bicycle, then it's definitely a solid brick. The converse need not be true actually. We'll talk about that in a bit. So, amongst the bricks families that you know, what is one that is definitely solid? Wheels. Wheels, right? K4 is the smallest wheel, but wheels in general, they don't even have a bicycle. How will you find two vertex-disjoint cycles in a wheel? Right? So, wheels are here. In fact, you can add multiple edges to wheels. They will also be here. Multiple edges anyways won't affect the solid property. So wheels are solid bricks. Any other family you can think of? There are other families of bricks we have talked about in the past. There is one family where you won't be able to find a bicycle. Odd bicycle. You will find bicycle but not an odd bicycle. Did you say ladder? Put adjective before that, then you are right. Mobius ladders. Mobius ladders. Mobius ladders, it's not so easy to see, but there is actually a nice way to see it. We will talk about that later. It has some topological concepts that I need to kind of revise before I teach those things. So Mobius ladders are actually solid. You can convince yourself that in the Mobius ladder, you can find vertex-disjoint cycles, but not an odd bicycle. That's not possible. Right? Okay. Anyway, so those are some examples. Okay. So that's okay. So in fact, I'll just probably introduce a terminology. Odd intercyclic graph. We will talk more about this in a future lecture. I just want to define it. This is basically coming from SGT. In fact, I took the SGT terminology from here. So in SGT writing exercise, you basically characterize the intercyclic three connected graphs using Tutt's-Wheel theorem, right? Which basically means that they don't have a pair of vertex-disjoint cycles. This is the graphs that do not have an odd bicycle. These are graphs free of odd bicycles. So you don't have a pair of vertex-disjoint odd cycles. And what we observed is that in the case of bricks, for example, yeah, so maybe I should mention why we are considering bricks. Yeah, observe that. So I'll just take an observation. Every odd intercyclic brick is solid, because solid brick should have vertex-disjoint odd cycles. So every odd intercyclic brick is solid. In fact, you don't even need brick here. Every odd intercyclic matching covered graph is solid. Right? That includes bipartite graphs. Bipartite graphs definitely are odd intercyclic. Right? But this also includes wheels and Mobius ladders, for example. Okay. All right. But here is one more thing I want to state. So here is a decision problem. Given a matching covered graph, decide whether it is solid. Is it in NP? Is it in co-NP? Which one is clear? Which one is not clear? Okay, you can raise your hand. NP, co-NP. So the point is, basically, it is easy just from the definition and by things we know. So we just need a certificate. We don't need to know how to find the certificate, right? We are not talking about P here. So NP and co-NP are just about certificates. So if the matching covered graph under consideration is not solid, that means that it has a separating cut that is not tight. I will just give you that separating cut. To check that it is separating, you just compute the contractions and check the contractions are matching covered. That is easy, that is polytime, right? And to convince you that it is not tight, well, I will simply give you a perfect matching that meets the cut in more than one edge. Right? So I can give you the cut and the perfect matching, and you can now check efficiently that it is indeed a separating cut that is not tight. Right? So therefore, the problem belongs to co-NP. This decision problem belongs to co-NP, and the certificate is just C, M, where C is a separating cut and M is a perfect matching such that M intersection C is greater than 1, therefore at least 3. become odd cut. Right? So, however, what is not at all clear is why this problem should be in NP. How do you convince somebody that every separating cut is tight? Right? There may be many separating cuts. For example, in a complete graph on 100 vertices, every 3 vertices comprise the shore of a separating cut. In fact, any odd number of vertices is the shore of a separating cut. Of course, complete graph is easy, but yeah, good.
This is a vertex which is part of every odd cycle.
Sorry, can you repeat that?
I mean, there exists no disjoint odd cycle.
Oh, but it's not if and only if, right?
I mean,
right.
If there is a vertex part of any two this odd cycles,
Good.
to try this NP and say.
Right. The problem is this odd cycles, as stated, it doesn't capture the solid property. It's not if and only if.
Yeah.
So it's not clear, it's not in fact true, that a matching covered graph is solid if and only if it does not have an odd bicycle. That's the problem. So yes, to decide whether a matching covered graph is odd intercyclic, that is actually easy. It's not super easy. There is a deep result. I don't want to talk about that result today because there's some topology involved. I need to prepare a bit for that. So I'll skip that part today. But yeah, the main problem is odd intercyclic is not the same as solid. If these were same, then this problem would actually be in NP. So in fact, this brings me to some story. So, but let me see. First, let me tell you another important point which I have been wanting to make. Yeah. Let's see. I want to state one more corollary from a previous chapter. So this decision problem, whether it is in NP or not, is actually open. This is an open problem, and therefore, of course, it is also open whether it is in P or not. Right? So, but here is a nice thing. Like many problems in matching covered graphs, this problem actually reduces to bricks. So that is what I want to state next. Corollary 4.16, which is an immediate consequence of one of your exercise problems where you proved theorem 4.14. So this follows from theorem 4.14. Maybe I'll state it in a bit. It is related to this this cohesive collection of cuts. Okay. But anyways, so let me just tell you what the corollary is. G is a matching covered graph. D is a tight cut. If G has a separating cut that is not tight, then one of the D contractions of G also has a separating cut that is not tight. What is it? Yeah. Then one of its D contractions also has a separating cut that is not tight. This follows immediately from theorem 4.14, which you proved in the assignment 2. It basically says, you have two separating cuts, C and D. You can think of them as crossing, but the laminar case is easier actually. Then what you proved is M intersection C plus M intersection D is equal to M intersection I plus M intersection U. What was the other assumption you need? You have two separating cuts and they are cohesive. C comma D is cohesive. Cohesive is always true when one of them is a tight cut. If one of them is a tight cut and the other one is separating, may or may not be tight, then C comma D is actually a cohesive collection. That follows easily from the definition of cohesive. Then you actually prove that I and U are also separating cuts. The entire collection CDIU is cohesive, and this equation holds. Because here I am assuming that I have a separating cut that is not tight, I can assume that one of them is separating but not tight. So I can get a perfect matching where this will be 3 or more. This will be 1 because D is a tight cut. Now one of these has to be greater than 1. Therefore one of them will be a separating cut that is not tight. So this is basically part of theorem 4.14, and from this you immediately get corollary 4.16. Right? Anyways, that was a bit fast, so I will leave it as a DIY. And a consequence of this is that a matching covered graph is solid if and only if each of its bricks is solid. Again DIY. The bricks can be computed in polytime thanks to Edmonds, Loaz and Poly-Blank. Therefore, for this decision problem, you simply need to consider bricks. Instead of matching covered graphs, you can replace it by brick. If you solve it for bricks, you have solved it for all matching covered graphs. Right? So that's a standard phenomenon in the theory of matching covered graphs, as you have seen earlier. Okay, good. Yeah. Okay. So that is actually the reason why the chapter or the title of this chapter is actually solid bricks. Rather than saying solid graphs, they just call it solid bricks because that's basically what matters. Okay. So why are we all of a sudden talking about solid graphs? What is the connection with the earlier chapter, which was the perfect matching polytope in particular? That's the main thing we discussed. Turns out there is a close connection between solid graphs and the perfect matching polytope. To explain this connection, we will talk about two more polytopes related to the perfect matching polytope. Yeah. Let's see. So let's recall the perfect matching polytope. Well, we have two definitions. The standard definition, convex cell of all perfect matchings, or we can now also use Edmonds definition. Right? So it is basically the set of all vectors that satisfy non-negativity, degree and Edmonds constraints. X of E greater than or equal to 0 for each edge, x of partial of V is equal to 1 for each vertex, and for each odd cut we want this to be greater than or equal to 1. Yeah, this is a perfect matching polytope. What we will now do, we will first of all we will restrict ourselves to matching covered graphs. Okay, so from now on, I am only restricting myself to GE matching covered. So in fact, I can remove odd S and I can just make it odd cut. Is that okay? And of course, the trivial odd cuts don't matter because they're already taken care of here. So you can, in fact, you can restrict yourself to non-trivial odd cuts. Right? Trivial ones is already equal to 1. So why do you need greater than or equal to 1? You don't need it. Right? Is that okay? Fine. So this is the perfect matching polytope as far as a matching covered graph is concerned. Okay. Now what we'll do is we will consider two relaxations of this polytope. In the same spirit as we did earlier, we considered relaxations. So the first relaxation is we will impose this condition with equality only for tight cuts. Anyways, for tight cuts, it will hold with equality, as we actually discussed earlier in the first part of today's lecture. Right? So in fact, for tight cuts, this will be equality only. You don't need greater than or equal to. You can actually put equality. Right? So this is what we are going to call the tight perfect matching polytope. So this is they call it the tight cut perfect matching polytope for the lack of a better name. So this is basically all vectors that satisfy xe greater than or equal to 0 for all edges, and x of partial of t, or maybe partial of s only, equal to 1 for all tight cuts partial s. Yeah? Do you all agree that this is a relaxation of this one? Tight cuts includes trivial tight cuts. So it takes care of this, and basically instead of this, we are just putting equality for the tight cuts. Anyways, they will hold with equality. Yeah? In the perfect matching polytope, anyways, they will hold with equality. Okay? But we are dropping the non-trivial odd cuts. Those we are not considering here. Right? Is it okay? For example, let's take a concrete example. For our standard graph, if I may call it. Do you see a vector that belongs to this fellow but not to this fellow? Yeah? Do you see a vector for this graph that belongs to this relaxation but it does not belong to this? We are only considering the tight cuts. We don't care about the other odd cuts. Right? So, yeah? You all see it? Half, half, half on the triangle edges. If I put half, half, half on the triangle edges, it satisfies the so-called tight cut perfect matching polytope, but it doesn't actually belong to the perfect matching polytope. So in that sense, what is clear is that in general, for a matching covered graph, the perfect matching polytope is a subset of the tight cut perfect matching polytope. Yeah? Okay. But I told you we'll consider two relaxations. We'll relax this further. We will just drop all the odd cut constraints. We will put this equality for 1 only for the trivial cuts. This is the original two conditions, non-negativity and degree constraints. Only that. That is generally called the fractional perfect matching polytope. And maybe Meghna has discussed it, or maybe Shaunaka discusses it in this course, I'm not sure. Right? So we will just consider the first two constraints. Okay? So maybe I will not even write it again. I will just use another chalk. So if I just consider these two, non-negativity and degree constraints, then we will call it the fractional perfect matching polytope, poly star of G. This is actually more standard in the literature. The tight cut perfect matching polytope, you will not see it in the literature as much. This is very well studied in the literature. This is called the fractional perfect matching polytope. I also like to call it the Birkhoff von-Neumann perfect matching polytope. I'll explain why that later. Okay? So do you all agree that this is a subset of the fractional perfect matching polytope? Yeah, this is the most relaxed of the three. Of course, I haven't given you an example to show strict containment here. Right? This one is strict containment because of this example in general. Right? Yeah. Okay. So you can ask the question, when do these hold with equality? When does this hold with equality? And when does this hold with equality? Okay, you can also ask only for this, I will not go to that. We will ask, when is the perfect matching polytope equal to the tight cut perfect matching polytope, and when is it equal to the fractional perfect matching polytope? Turns out the answer to both of these questions is related to solid graphs. Okay, I'll just state it, we will not prove it today. I'll just tell you what the result is. So coming up, for a matching covered graph G, these two are equal if and only if G is solid. The perfect matching polytope is equal to the tight cut perfect matching polytope if and only if G is solid. This explains why this is the smallest matching covered graph that is not solid. Non-trivial separating cut that is not tight. Right? So this is the reason why this proper containment happened in this example. Yeah? Because it's not solid. And if you want the perfect matching polytope to be equal to the fractional perfect matching polytope, which of course means that everything has to hold with equality. If these two are equal, then of course this is sandwiched between them. It is also equal. Yeah? That happens if and only if G is solid and its B is equal to 1 or 0. This is G is solid and the number of bricks is either 0 or 1. Either it is bipartite or it is a near brick. And when it is a near brick, its unique brick has to be solid again because of theorem 7.1. Right? Right? This is what I generally call the Birkhoff von-Neumann graphs. So if you may have seen some of the papers or talks, this is generally called, well, not generally, one of my papers we call it Birkhoff von-Neumann graphs. The reason we called it Birkhoff von-Neumann, one is because it sounds fancy, but the other reason is because bipartite graphs, for bipartite graphs, the fact that these two are equal is well known for many decades now. Yeah, so as I was saying, the fact that these two are equal for bipartite graphs is actually known for a very long time. That is due to independent results of Birkhoff and of von Neumann related to doubly stochastic matrices. Don't ask me what they are something. They proved some results about doubly stochastic matrices, and a corollary of that is that the two are equal for bipartite graphs. So bipartite graphs are Birkhoff von Neumann, has been known for a very long time, but the class of Birkhoff von Neumann graphs is larger than the class of bipartite graphs. So if we go back to the original drawing, what we see is something like this. Bipartite is contained in Birkhoff von Neumann, which is further contained in solid. Okay, and now let me give you one example of a graph that is solid but not Birkhoff von Neumann. It's the graph we drew earlier in part 1. Of course, this is solid because all of its bricks are solid, K4, but it is not Birkhoff von Neumann because it has 2 bricks, right? And that is not allowed in Birkhoff von Neumann. So this is an example of a graph that is solid but not Birkhoff von Neumann. And you can observe with not much difficulty that a brick is solid if and only if it is Birkhoff von Neumann. So if you assume these results and this definition, then you can check that a brick is solid if and only if it is Birkhoff von Neumann. So in the case of bricks, these are exactly the same sets. Solid bricks are the same as Birkhoff von Neumann bricks. And for both of these open problems, given a matching covered graph, decide whether it is solid, decide whether it is Birkhoff von Neumann, it reduces to bricks because of what I have stated here. So it reduces to bricks, and in the case of bricks, they are exactly the same. So this is the main open problem that I wanted to state today. Yeah. Okay. Yeah, there is more things I want to state, but we are also at 4:15 p.m. So let me probably stop here, and we will continue tomorrow. Are there any questions or concerns? Yeah, we are having 3 lectures this week: Monday, Wednesday, and Thursday. Yeah. Yeah. Any other questions, concerns, anything? So yeah, there is a lot of info. Try to go through it because definitely there is a lot of new concepts, and see if you can make examples and familiarize yourself with these new concepts. Right? Yeah. Okay. Thank you. That's all for today.